Anyone? That is on somewhere around 23rd or 24th of June, isn't it? So almost 2 months ago, almost 2 months ago, 6 weeks, right? So can you all remember what we have learned? Can you all remember what we have learned? Can you all remember what we have learned? Yes? Can you all remember what we have learned? No one? Yes? Tanusha, no one is speaking. Why? After the exam, everybody freeze. Hmm? So we started with a course on design, experimental design. Then we discussed about a few things. Uh, these are your basic information from your side. What are the outcomes and expected outcomes, and what is the objective, and also the course content. Then we said the three most important principles in experimental design, and we talked about two of them completely. One is randomization, the other one is replication. Randomization and replication. So randomization is done by, why it is done? It is to get the unbiased estimate. We always get the estimates, right? We don't know what is the actual value, but we estimate. So in the randomization, we do randomization to obtain the unbiased estimates. How to do the randomization? Without giving any priority to any of the experimental unit, we give the treatment. That is called randomization. We learn about that, right? Then replication. Replication means we are repeating the same experiment again and again. Same experiment means same treatment. Suppose if you have a few treatments on fertilizer, then suppose let's say you have zero fertilizer, 10% of the fertilizer as second treatment, 15% of the fertilizer as treatment, 20% of the fertilizer as third treatment, and so on. When you apply this treatment, you can apply into different experimental unit. Not only one unit, you can apply to several number of experimental units. Why it is done? That is to obtain the error variance. That is to obtain the error variance. What is the definition of error variance? If two units, if two experimental units have been treated with the same experiment, the variability between those two experimental units, so we say two experimental units, they have been treated similarly with the same treatment. If you measure the variability between these two units, then that variability is actually called as error variability. So the units which has been treated similarly, if we find the variability in those units, that is basically called as error variance. Then at last we talked about control of experimental error or control of unexplained variable. How we can control any experiments before we do the experiments. Can you remember when I defined the term statistics in your third year? We said statistics is a uh, subject dealing with data. So there are 4 steps. What are those 4 steps? Can you remember? Planning, planning, then doing the data collection, then classifying the data. Ultimately, you analyze and interpret the data. 4 steps. We have learned this. It is in your notes. So the planning, when you plan an experiment, you have to plan all these aspects: randomization, right? Replication, randomization, replication, and what do you call uh, uh, control of experimental error, right? So randomization, replication, and control of unexplained variable, right? Uh, so we will look at the control of unexplained variability, because randomization and replication we have done already. We learned already. Mm, yeah. So we will go to that slide. Uh, right. So basically, randomization, we already said. More important keywords are experimental units, right? Uh, we explain all these, how the treatment will be allocated for each experimental unit on a random basis, which is called as randomization. Then replication, you repeat the same treatment more than once, which is called as replication. So basic information on replication is to obtain the error variance. To obtain the error variance. The number of replications, how we determine the number of replications, that is depend on few key informations that we have discussed, and also how the error make influence on our study. So we have given a dartboard. Using this dartboard, we have explained how the precision and the biasness is important. When you talk about precision, it is dealt with replication. If you have more replication, more precise. Similarly, if you do good randomization, that is dealt with accuracy, right? So replication and the randomization will lead to precision and unbiased estimates. Then we talked about how this variability can be partitioned. So some of the variables which can group into explainable variability, and the rest of the variables, portion of the variable, can be partitioned into unexplained variable. So explain and unexplained. Why this explain and unexplained is important is that when you do the experiment, we have test statistics. So based on the test statistics only, we make a decision whether we can accept the null hypothesis or whether we can reject the null hypothesis, whether we accept or reject the null hypothesis. So to make that conclusion, we have to formulate our test statistics. So in this experimental unit, the test statistics is based on our F distribution, we know what is F distribution. It's not a normal distribution, it is a skewed distribution. This test statistics, actually it is between the ratio of the mean square of treatment and the error. So it is the ratio between the mean square of treatment and the mean square of error. So that is why this is important, right? Mean square error is important because we always compare the quantity, or in other term, variation of the treatment with the unexplained variation. So that is how the comparison is always made. So whenever the unexplained variation is lower, whenever the unexplained variation is lower, so what is the advantage? When we have this is low value, if you have, I mean, even if you don't touch the explained variation, if you have less value for unexplained variance, what will happen for the calculated value? What will happen for calculated value? Calculated value will increase. So if the calculated value increases, what is our decision making process? This is the F distribution. This is the F distribution. So let's say this is our rejecting region. This is our rejecting region. So F value starting from 0 here goes up to infinity. So whenever the F value increases, definitely we are falling into the rejecting region. So that means we are coming to a conclusion that there will be some treatment effects. So the treatment effects can be identified easily when the unexplained variation is less. But on the other hand, if the unexplained variation is very high, what will happen to the F value? F value will be goes down. If the F value goes down, what is the problem? We fall into a non-rejecting region. This is non-rejecting region. This is non-rejecting region. This is rejecting region. So if you fall into non-rejecting region, what is the problem? Even though there may be some effect due to the treatment, however, because of this test statistics, we come to a conclusion that there is no any treatment effect. There is no any treatment effect. That is purely because if the unexplained variation value is high. So that is the reason why we want to control this unexplained variation. As far as we control this unexplained variation, it is good for the experiment results. Right? Is it clear? Is it clear? Right. So what is happening basically, based on the this F value, when the F value goes upper and upper, right? When F value goes upper and upper, so this is the rejecting region. So when the F calculated value goes higher and higher than the table value, we will fall into rejecting region. This is our rejecting region, right? Uh, yeah. Just a second. Huh? Uh, yeah. So that is the importance of reducing the unexplained variation, right? So in that respect, how we can control the unexplained variability? How we can control the unexplained variability? Can you all see the screen? I didn't put into the presentation mode. Can you all see? Yes. Can you all see? Tanusha?
Yes, sir.
Yes, sir.
Right, okay, fine. Right, I explained some of these facts, control of unexplained variability. First one is having the homogeneous or heterogeneous situation. Depend on the situation, we'll have to apply what design that we propose, right? Uh, Suppose, let's say, what do you mean by homogeneous? When you take a class, is it a homogeneous? No, class is not a homogeneous. Why? You have male and female as an example. So when you apply some treatment, we'll have to be careful because male and female. All right. Similarly, let's say you are applying treatment to variety. Already variety means it is heterogeneous. Why varieties are heterogeneous? Within the variety it is homogeneous. Between the variety it is heterogeneous. Why? Can you tell me why between the varieties we can call it as heterogeneous? Anyone? Because they are showing some different characters. That's why we call it as variety, isn't it? Maybe some variety shows high fruit size, some variety shows taller bushes, some variety shows larger grains, some variety shows the composition of the fruit is different. So that is why we call it as variety. They are not uniform. If they are uniform, it's a homogeneous. Otherwise, maybe some difference in morphological character. So that is heterogeneous. Then we said gradient blocking. We'll talk about this later in detail. What is this blocking? When there is a gradient, I simply took an example as far as I remember. Uh, uh, when you have a slope, right? For example, the land is, you are cultivating in the land. If you go to upcountry area, right? So in a hilly area, something like this, so you have a different position. For example, I take position A, B, C. Can you tell me about the position of A, B, and C in terms of their fertility in the land? What do you think about the fertility of the land? Which uh, which which is having high fertile? Which is having high fertile?
C.
C is having high fertile. Why? The answer is correct. Why?
If it is a runoff or erosion, the nutrient will be lost from A and
Yeah, deposited in the
and C.
low. Yeah, deposited in the lower part, so that normally we get more alluvial type of soil in this area. So here the fertility is high. Here the fertility is low. So now we can't treat this land, also this land in a similar way. If you do a fertilizer trial, why? Why? Because already in this land portion of the land, the fertility is high. If the fertility is high already in this land, that will also give some effect. So in this land, the fertility is low. So this situation is called as heterogeneity condition. Let's take a laboratory, right? Laboratory. I'm not a good artist. I'm just drawing a laboratory. Let's say this is window or door or whatever. This window and this door. It is a laboratory, right? So inside the laboratory, I'm taking the cross section. What do you think about this laboratory? Let's say, assume this is A, assume this is B, assume this is C. Three different positions. Tell me where the temperature is high, whether the temperature is different in this. Let's say it is a concrete floor, so no problem with the ground, right? Let's say a laboratory or plant house, which is concreted at the bottom. So can you tell me, is there a difference between these positions A, B, C in terms of atmospheric or sorry, rather than saying atmospheric, environmental factors? Let's say temperature, the RH, because this is a closed house, like a greenhouse, right? So this is a concrete. This is made up of concrete. So no variation on soil. Then what about the environment variation? What do you think about temperature between these 3 points, A, B, and C? Temperature, let's say RH, light. What do you think about it? What do you think about that? Is same in ABC or different? Temperature, is it same in ABC or is it different? What about RH? Is it same in ABC or light? So we can assume that the temperature or RH or light at ABC more or less same. More or less same. So this condition is called as homogeneous condition. Homogeneous condition. Right? This is considered as homogeneous condition. Right? Let's see. All right. So that is homogeneous and heterogeneous situation. Then in animals also we may get heterogeneous conditions. If you take age, breed, then we'll have to do the blocking. We will come to that the term when we talk about the special type of design called blocking design. Then type and number of treatments. So suppose this I have talked last time also. If you have large experimental units, right, then we don't have problem. But if you have, let's say this is, I have 4 treatment, right? I have 4 treatment. Let's say I have 4 treatment. If you accommodate all 4 treatments here, right? Let's say 5 treatment. 5 treatment. So here 1, 2, 3, 4, 5. I can accommodate all treatment, all the treatment. So it is called as complete block design. Suppose I don't have enough space to accommodate all 5 treatment. I have space only to accommodate 3 treatment. So out of 5, I can accommodate only 3, maybe 1, 2, 3. So treatment 4 and 5, I cannot accommodate in the same block. Therefore, it is called as incomplete block design. Write down what is CBD. I put it in simple form. CBD means complete block design. Complete block design. So this is a complete block design. Example for complete block design. When you have 5 treatment. If you have, let's say, just a second. This internet's giving problems. Right? So again, if you have same 5 treatment, we cannot accommodate all 5 treatments in the block. So that we can maximum accommodate only 3. So we'll have to decide what 3 that we can accommodate. So in that situation, it is called as incomplete block design. So this is called as incomplete block design. So depend on the number of treatments, we can decide, uh, right, whether we go for complete block design or whether we go for incomplete block design. Then we can have, depend on what experiment that we are carrying out, we can go for factorial experiments. So we will talk about factorial experiments later. Right, maybe this is the place where I have stopped last time. Is that? Some of you don't remember. Right. The control of unexplained variability continues. The number of replicates, how we decide the number of replicates. Right? When you talk about number of replicates, what do you mean by number of replicates? Right? Now I'm going to do a small research. Right? I'll take a field. This field with chili, I'm going to do 4 treatment. Let's say 4 treatment. One is organic fertilizer, the other one is organic fertilizer with 50%. Oh, first I will take 25%. Right, organic fertilizer plus 25% inorganic fertilizer of what we have recommended. The third one, organic fertilizer plus 50% of recommended inorganic fertilizer. The fourth one, organic fertilizer plus 75% inorganic fertilizer. You see, do you think all the treatments are same? This is only organic fertilizer. This is organic fertilizer plus 25% of inorganic fertilizer. This is organic plus 50% inorganic. This is organic plus 75% organic. These are called as treatments. So how many treatments we have? How many treatments do we have that we want to test it? 4 treatments. Right? These are the 4 treatments. Let's say I will just put it as T1. This is T1. This is T2. This is T3. I hope all of you are writing what I am writing, right? This is T4. So hereafter, I am not going to talk about organic plus 25% and so on. I will talk in terms of T1, T2, T3. Right. Now, this is the plot. I'm going to test with chili plant. What is the crops? Chili. I'm going to first one. This is in the field, right? This is in the field. Here I'm applying first one randomization. So first one T3, T2, T4, and T1. This is what we call as randomization. Without giving any priority, I have just allocated. Doesn't matter. So I am applying T1, T2, T3, T4 for different plots. So these are the plots, right? Maybe in Tamil, you may call it as Pati, right? In Sinhala, Mona, again. Kutwak kila kiyan pula. Any Sinhalese? Huh? Kodi Kotwak, right? So in this small plot, let's say this is 3 meter width. This plot is 3 meter width, and length is 2 meters. So what is the area of this one single plot? Roughly 6 square meter. So in 6 square meter, how many chili plants that we can plant? What is the spacing of chili plant? Anyone? I will catch who are doing agronomy. Who is doing agronomy? I want to. I will get the list now. Huh? Tell me tell the group of people who are doing agronomy. Yeah.
30 into 60.
Right. Okay. Some value. Huh? 30 into 60 meter or what?
Centimeters.
Centimeters. Yes. Good. Always you'll have to tell with the unit, right? So 30 into 60. Now tell me how many plants we can accommodate roughly.
6 meters.
Huh? Roughly how many plants we can accommodate if this is the space. Huh?
100.
Huh? How many plants we can accommodate? No problem. Just answer. You can put it in the chat. You can answer through chat. Anyone can answer through chat. That is why we are having chat. Huh?
33 plants.
33. How did you get that value?
Area.
Land area.
Land area over.
What is the
Over
land?
spacing.
What is the land area?
6 meters square.
Yeah, 6 meters square. How we can write that? In centimeter or otherwise, let's say
Centimeter.
6. Yeah, we will write in meter. So this is 6 divided by 0.3
into
0.06.
Yeah. What is the answer?
33.
33. This is yes.
33.
Yeah. 0.3 divided. Yeah, 33. Roughly 33 plants. Roughly, yeah. Don't worry about how the arrangement. So now I have how many plants here? 33 plants roughly. So every plots, right? So that means we are planting in a normal way, right? 33 plants. Let's assume we have roughly 33 plants. Now tell me the number of replicates, the number of plants per plot. This is what our concern is. How many plants per plot? 33 plants per plot, isn't it? So these 33 plants in this plot will receive T3. This 33 will receive T2. This 33 will receive T4 and this 33 will receive T1. You understand? Now, the number of replicates has to be decided by the destructive sample. What do you mean by destructive sample? When you do experiment, right? After giving all this treatment, you want to measure the progress of the plant. Maybe you may measure root length or dry weight. If you want to measure the root length or dry weight, what should we do when the plant is in the field? Can you measure the root length or dry weight without removing the plant from the field? Yes or no? If you don't answer, I don't continue. I will wait till the answer comes. Can you measure the root length without uprooting the plant? No. It's a common logic, huh? I mean, can you measure the root length without removing the plant from the field?
No.
No. Similarly, dry weight, total dry weight of the plant. Can you measure the dry weight without taking from the field and putting into the oven and that process? Can you? Yes. Can you do it?
Can't.
We can't. So that is called as destructive sample. That is what we said, destructive sample. So, for example, some students, I mean, even when you come to your research, I mean, rather than saying students, some researchers, they want to measure the dry weight in the first week. First week, right? They want to measure the dry weight in the second week. They want to measure in third week, fourth week, fifth week, and so on. Sixth week, seventh week, eighth week. So for 8 weeks, they want to measure. So what shall we do? Do you think this plant response is same as this group of plants?
No.
No. Why?
Difference in fertilizers.
Yeah, different.
In fertilizers application.
Exactly. So we have applied fertilizer differently, different proportions. So we can test only these 33 plants for that given fertilizer recommendation. Right. Now, what in the first week, if I remove, I mean, for sample, if I take 4 plants, I take 4 plants in the first week. For the second week, again, I take 4. The third week, again, I take 4 as an example. So, right, I took 4 in the first week. So, how many remaining? I have uprooted 4 plants in the first week. So, how many plants remaining?
70.
29.
Huh?
29.
29. So again, yeah, again you take, you can answer in the chat. Huh? I can look at it in the chat also, people who are reluctant to answer. You can harvest, I mean, uproot the second group, 4 plants, the second week, third week, and so on. So at the 8th week, again you are harvesting 4 plants. So how many plants remaining after 8th week?
Only one plant.
Only 1 plant. Now, when you do the fertilizer application, these are some of the root length, dry weight are some kind of additional measurements. But ultimately, what we want to measure from this, ultimately, after giving all these fertilizer, what is the economic product of chili plant? What is the economic product of chili plant?
Chili.
Is it, huh?
Chili.
Yes,
Chili.
yes, I couldn't hear properly. What is the economic part of the chili plant?
Chili fruits.
Huh?
Fruits.
Pots, yeah, chili pots. Right. Fruit or pots or whatever it is. Ultimately, we want to get the yield. I will put it as yield, whatever the yield. Chili or rice, I mean paddy, or in any cases, we want to have a chili plant. I mean final yield as the ultimate objective, right? So that is very important. If you don't have plans to measure, right? If you don't have plans to, because we have now only one plant to measure, right? You have only one plant to measure yield. You have taken uprooted all the plants for dry weight or root length or whatever it is. Ultimately, you have one plant to measure the yield. Is it a good criteria to measure only using only one plant? No, we need several plants to measure. That is one thing. Second thing, do you think all 33 will survive? Suppose if 5 plants died due to, let's say, at the beginning of the planting, maybe due to what do you call fungus, or due to maybe leaf curl diseases, 5 plants are affected. So we'll have to remove that 5. So ultimately, we don't have enough plants to do the experiment. So that is why at the beginning, we'll have to plan it. We'll have to plan how many replicates that we want, how many plants in a plot that we want. All these we'll have to plan at the beginning. So this is what I said, how frequent the data has to be collected. For example, you see here, every week we are collecting data on plants for their root length or dry weight. So all these have to be planned at the beginning to decide the number of replicate or number of plants per plot and so on. Right? Is it clear? So that is important. Then good experimental design. So that we will come to that. The appropriate design has to be proposed. Appropriate design has to be proposed. We will be learning those designs one by one. So you will realize how these designs fits for the different situation. So when you talk about good experimental design, depend on the situation, experimental site. So that means depend on the area that you are going to do the experiment. We can decide, for example, if the site is the land, if the site is greenhouse, or if the site is a glass house, or if the site is a laboratory, or if the site is closer to the road, right? So likewise, I don't know how many of you are in the living closer to the first highway of Sri Lanka. Anyone? Anyone from maybe not Tamil students, some Sinhala students? What is the first highway in Sri Lanka? If you don't know Sri Lanka history, no point of living in Sri Lanka. What is the first highway? Highway. From where to where?
Colombo, Patna.
Colombo?
Patna.
Is that first highway? I'm talking about highway, where you nowadays pay, and we went through highway. Can you remember? We went to Paliagoda.
Paliagoda to Patna.
Are you sure?
Yeah.
Are you sure?
Colombo to Goal.
Colombo to
South.
Goal.
I'm asking the first highway, not
Colombo to Goal.
yeah. Anyone?
Colombo to Goal.
Yeah, E01. It is the number somebody has said. Yeah. What is E01? Colombo to Goal. Yes, that is the first highway in Sri Lanka. I mean, they have laid the foundation for highway in Sri Lanka maybe during Sirimao time. That is to Colombo to the airport, but never materialized. But the first highway is Colombo. Rather than calling it is Colombo, it is from anyone? Not Colombo, right? Anyone knows exactly where I start from?
Kottava.
Yes, Kottava to Goal, right? Still, you cannot call it as Colombo because Colombo, from Colombo city to Kottava, you'll have to travel maybe 25 kilometers, right? Okay, right, doesn't matter. During that time, after developing that highway, there was a speciality of the fields surrounded by that highway. They found, agriculture department found, just a second, are you all seeing? Something went wrong on my screen. Right? Can somebody guess what has happened? They found that the paddy fields closer to the highway have given slightly higher yield than the neighboring field. Can somebody guess what was the reason? I don't know, maybe that time you were not in the university, so you all were not interested in that news when it was appearing. Anyone, any idea why? Because can you remember in the highway, almost for more than 12 hours you can see the light in the night, the street light that is switch on, right? Because of that light, the nearby near to the roads, the paddy fields have produced high yield that they have observed. So this is an observation, right? So what I am saying is, so when you design good experimental design, you'll have to look at the site, what is happening, whether that site is suitable, whether that site is influencing the treatment, right? So ultimately, if you design experimental design closer to that highway, what will happen? The paddy yield will increase automatically. You come to a conclusion that is because of our treatment. No, it is because of the sun, the additional light. Do you understand? So we'll have to have a good knowledge how to plan, right? Controlling other factors. The number of treatments, number of replicates has to be decided, right? That we have seen also earlier. And further, block size. So this is the block size. What do you mean by block size? Let's say in early example, we had 4 treatment, this organic fertilizer and so on. We have 4 treatment, right? One is organic fertilizer, the other one is 25%, 50%, 75% addition to that. So this is how many treatments were there? Let's say T3, T2, T4, T1. How many treatments were there? Sorry, T1. Huh? This is T1. How many treatments? 4 treatments. In our early example, 4 treatments. So the block size, when you say block size, this is one block. This is called as one block, right? Let's say I will block 1. This is called as one block. So what do you mean by block size? What do you mean by block size? Size of the block mean, so here it is block size. Usually we give it as K. So how many plots are there in one block? 1, 2, 3, 4. 4 blocks. 4 block size is 4. So this block size is 4. Right? Suppose if I have 10 treatments, if I have 10 treatments, can you guess what will be the block size? If I have 10 treatment, if I want to accommodate all 10 treatment in one single block, how many or what is the size of my block? Anyone?
10.
10. Yes, 10. It is 10. Good. Now, let's say this is block size 4. This is block size 10. Why we have block size 10? Because number of treatment is high. So we say this is block size 25. I don't draw all these because you can draw 10 pieces, right? Takes time. So in another case, we have 25. So what can you say about, all right? What can you say about which one is block size is larger? Here the block size is less because only 4. Here block size is 10. Here block size is 25. Now can you tell me which one is called as large block size? Which block is having large block size? Definitely this block is having large block size. So if the block size is becoming larger and larger, what will happen? The variability will increase. Why? Because, for example, if it is a small block, in early example, this is 3 meter, this is 3 meter, right? This is 2 meter. Can you remember in early example, this is 3 and 2. So what is the total length of the block? For this total length of the block, how many meters?
8.
8 meter. So for this, if you have 10 treatment, if the
20.
block,
20.
20. What about this?
50.
50. Right. Now look at here, this is 8 meter distance. So if you consider 2 points, let's say A and B. So what do you think about the variability between these 2 points compared to the other situations, other 3 situations? So here A, here B. Which has more variability comparatively between these 2 points, A and B? Yes?
B.
No. My question is, this is situation 1. Let's say this is S1, situation 1. This is situation 2. This is situation 3. So my question is, where the variability is high between A and B, whether it is in
Situation
Situation 3.
situation,
B.
yes, situation 3. Why? Because the block size is larger, very large block size, very large block size. So if the large block size, what is the problem? We cannot maintain the homogeneity, right? So we cannot maintain the homogeneity, right? That is one of the problems, right? So we cannot maintain the homogeneity in large block size. So therefore, right, just removing some of the unwanted news hours. Right, large block size will have more variability, so we cannot have the homogeneity. Then we have a problem. So we'll have to decide what to plan for the design, experimental design. Right, next one is selection of experimental units or experimental material. Right, now the simple example is, now I'm going to do a small study. I'm going to do a small study on, let's say, germination of just a second. We will have a couple of minutes break. We'll have the 3 minutes break. Huh? 3 minutes break. Okay.
Okay.
Okay. Right. You had a glass of water. Right. We will continue. Uh, right. I said selection of experimental material. When you say selection of experimental material, I write it on the pad itself. I'm going to do a small germination experiment, right? Germination experiment. Uh, can you tell me what are the artificial growth hormones available in the market to induce the germination? Anyone?
Koche.
I don't know.
Gibberellic acid.
Okay, gibberellic acid. I don't know actually the trade names. Huh? Gibberellic acid. What else? Tell me three or four products at least name, but anyone? How about auxin? Will it induce the germination? Huh? Yeah. So anyone give some indole acetic acid? Somebody said. So I will put some. Any other answer? Let's say indole acetic acid. IAA. What else? Give me one more.
Naphthalene acetic acid.
Naphthalene acetic. NAA. Huh? Right.
NAA.
Right. Now I'm going to do a small germination test on papaya. Papo, right? Papaya. So now I want to collect some seeds, isn't it? For germination, I want to collect some seeds. Now, how to collect the seeds? Because my aim is to see which one is giving high percentage of germination, whether gibberellic acid or the indole acetic acid or naphthalenic acetic acid. So this is my this is what I want to find out. So for that, I have used papaya, for example, papaya. So how can I obtain the seeds? Because we need seeds to do the experiment, germination experiment. So where we can obtain the seeds? Right, now what I do is I'm going to Dambulla market. Right, I'm going to Dambulla market and I'm buying seeds. You can't buy seeds directly, so what we will do, we buy the fruits from the Dambulla market and bringing to the laboratory. I do the necessary procedure to obtain the seeds. Is it recalcitrant or orthodox? I'm asking too much of agronomy questions. Huh? Huh? Yes, yes. Answer is correct, I think. Again, I didn't hear properly. Is it recalcitrant seeds or orthodox?
Recalcitrant.
Recalcitrant, good. So it's a recalcitrant. There's a procedure how to extract the seeds from the fruit. Now I'm using that seeds to test the germination percentage using these three treatments. So I'm putting into 3 Petri dish, for example, 3 Petri dish. This is gibberellic acid, seeds with gibberellic acid, right? The other one is indole acetic acid, seeds with indole acetic acid. The other one is seeds with naphthalenic acetic acid. Now, can you tell me, is it a good experiment? I mean, experiment is, our objective is fine, no problem, no change in objective. Do you think, is it a good way that we have done this experiment? Starting from, yeah? Vaishnavi, are you around?
Yes, sir.
Yes. Do you think, is it a good procedure? No, our objective is to determine the germination percentage of papaya. Germination percentage of papaya using these 3 available hormones: gibberellic acid, indole acetic acid, naphthalenic acetic acid. My question is whether our procedure is a good one, or if it is a good one, no problem. If you say if it is bad one, how we can correct it?
If we collect seeds from same fruit, it's good.
Why?
If fruits vary, the variety of
Exactly. Good. Thing is, we have already brought up fruits with a lot of variability. Maybe when I went to Dambulla market, you get fruits from Vavonia, Dambulla itself, fruits from Anuradhapura. If you mix all these fruits, there's a variation already within the fruits. All right. I mean, I simply said the location as well as even there may be variations in variety. What are the varieties available? I am not familiar. Red lady, I know, but others, what are the other varieties?
Ratna.
Yeah, Ratna. Okay, so there may be a mix of fruits. So already when you say variety, that means there is a variability already. That is how we separate them as variety. So after separating them as variety, again these fruits are causing some variability. If you bring those fruits and putting into the experiment, that is a problem because already they have the variability. Can you remember? Uh, uh, Initially, we said we want to control the rest of the variability. We want to evaluate the variability only due to these three hormones. Whatever the hormones that we are applying will create variability. So that variability is the one we want to evaluate. But on the other hand, the fruits which I have bought from the Ambula market have already created some variability. So this is a contradiction. So that is why we want to have an eye on the planting material, right? So eye on experimental material, planting material, for example, seeds, example, clone. So when you compare seeds and clone, which one is having less variability?
Clone.
Clone is,
Clones.
yes, clones having less variability. Why?
Seeds.
Seeds
It's
can be, pollination,
cross-pollinate.
So variability is very high. So you'll have to be careful what sort of planting material or experimental material that we are obtaining. So that is why, for example, in animal science, people who are specializing in animal science can think about it. Suppose I am going to do an experiment in 3 diet, 3 or 4 diet, let's say 4 diet. Let's say I'm testing only in the feed formulation. I'm protein as a protein supplement. I'm giving fish supplement, fish meal, right? Fish meal. I will put it as FN, protein supplement. That is one experiment. What are the other protein supplement? Let me know.
Soya bean meal.
Soya meal, blood meal. I'm also learning, right? After 35 years. Blood meal. What else?
Meat meal.
What meal? I didn't get it. The last one.
Meat.
Meat meal. I have never heard about it. Okay, I will put it as meat meal. Right. Fish meal, soya meal, a blood meal, and the meat meal. So this is what I am going to test it from pigs. For example, from pigs. Right. So what is the best way to select the animals from pigs? The best way is selecting the siblings. Do you know what is siblings? Brothers and sisters. What is the litter size of pigs usually?
8 to 12.
Yeah. So pigs are having maybe 8, more than 8 roughly, litter size. So ideal for this kind of experiment. So we can give the treatment. So, right. So first we can select 4 piglings for this experiment. Then from another litter we can select another 4 experiment, so that we can block. That is first block. This is second block. We'll talk about block later when we talk about animals block design. Right. So that is called as siblings. Why we choose siblings? Before applying these treatments, all experimental units should have the same character. No difference. All should have same character. So that is the expectation of sibling, right? Just a second. Right. So that is the expectation of sibling. Before we apply any treatment, we expect them to have less variation or no variation in other term. So siblings are the ideal. So siblings from one single litter would be better. Right. Right. Yeah. Maybe one more slide on this. Plot size and plot shape. Earlier we talked about this plot size. In our chili example, we took a plot size. Let's say, what is the plot size? We had 4 treatment, 3 into 2. So plot size is 3 into 2, that is 6 square meter. Suppose if I have another setup, 3 into 3 meter. So what is the plot size? 9 square meter. Per plot, it is 9 square meter. Isn't it? 6 square meter, 9 square meter. So what do you think about the plot size? This is increasing. Plot size is increasing. So if you increase the plot size, what can you say? How many plants that we can plant here? 33.
33.
Here? What about here? Roughly about 50. 50 or maybe wrong. 46? 15. Yeah. Anyone?
50.
Yeah, roughly about 50. Right? So now you see what has happened. If the plot size is increases, the number of plants that we can accommodate also will increase. When the plot size increases, the number of plants that accommodate also increase. What do you think about the variability if I measure among these 33? Let's say that is variability 1, that I am measuring the variability among these 33. Now I am measuring the variability among these 50. Let's say that is V2. What do you think about these two values? Theoretically. What do you think about these two values? Which one is higher, which one is lower? We learned this in first course. Where the variability is high, where the variability is low.
V2 is higher than V1.
V2 is higher than V1. Good. Why?
Block size is large, so variability also.
Yeah, block size is large. That is okay. But I'm focusing on the plants. How many plants in V2 and how many plants in V1?
Plant density high in V2.
Yeah. Don't worry about the density. Number of plants. Where the number of plants is high, density is same. Density is same. Why density is same? We didn't change the spacing. Spacing is same. So the density is same. Isn't it? Density is always given per unit area. Density is same. Plant density is same. Because we didn't change the spacing. If you calculate per hectare, this is 33. I mean, in that case also you can calculate for hectare, and in 50 also you can calculate for the hectare. Number of plants in V2 is high, so variability is high. Somebody said yes. That is the reason. The number of plants, because can you remember the sample? We talked about sample. Sample is very high. So when we increase the sample, the variability will reduce automatically. Right? So here the variability V1 is higher than V2. V1 is higher than V2. Right? So that is what I am going to show it to you here. So this is in simple term. The first diagram or the first graph, when you increase the plot size, now don't ask what is plot size. I have already explained. So when you plot, when we increase the plot size, what is happening to the variation? Decrease. Variation decrease. Right? But as a criteria, when you increase the plot size, variation decreases. But there should be a place to get the optimum plot size, the best choice of plot size. So the ideal is usually the cost to establish the plot is increases when the plot size is increases. The ideal place to look at the plot size is this, the intersecting point of the cost and the variation. So this is the ideal place to have the plot size for any experiments, right? Theoretically. Any questions? Right, that's all about the control of unexplained variable. Right, we discussed. So we will have to control all the unexplained variability to have a good way of handling the result. Clear? Okay. Right, now we are going to learn about the design. First of all, what is this experimental design? Right, what is this experimental design? The manner in which the experimental units are arranged or grouped and how the treatments are assigned to them. So in simple terms, when you say design, is it same as, let's say, housing? When you want to build a house, what is the first step that you do? You draw a plan. So how you draw a plan? Based on some kind of design, isn't it? So I want the study room here. I want the kitchen here. I want this living room here. I want the bedroom here. I want the toilet here. So it is a kind of design. Based on the design, we prepare the plan. So here also, based on the treatment, how these treatments are assigned to the experimental unit, that will reflect the experimental design. It is a plan actually. Before you do the experiment, you'll have to have a proper plan or map, kind of roadmap to start up with the experiment. So experimental design is the one which is giving the information about how these treatments are allocated for different experimental units. In simple terms, right? Right. Why this experimental unit is important? Why we want to have this experimental unit? Anyone knows who is this Fisher? Anyone knows who is in this Fisher? Sir R.A. Fisher. Actually, he's a statistician, lived in UK. He's called as nowadays father of modern statistics. Father of modern statistics, right? So he's the one found this F-test that we are talking about. All this treatment mean square divided by residual mean square. Residual or unexplained variability, which we have already talked. So it's F-test. So he's the one found that, right? Father of modern statistics. He's the one found this F distribution also. F distribution. Right. So what he has said, is, if you don't have a proper design before the experiment, right? If you don't have a proper design before the experiment, then it is similar to asking a doctor to do the post-mortem, right? Everybody knows what is post-mortem. Asking a doctor, it is similar to asking a doctor to do the post-mortem examination, and due to what reason that particular experiment has failed, right? Or due to what reason that particular man has died, right? So due to what reason that particular man has died. So it is similar to that. If you, without having this proper experimental design, if you take only the outcome of the data, if you just bring the data to the statistician, right? If you bring the data to the statistician cannot recorrect the data again. Why? Because you have not obtained the proper way of getting the data. So to call the statistician after the experiment is, that means if you call a statistician after the experiment, that means if you give only the data after collecting the data to the statistician, right? It is similar to, it is same as done maybe no more than asking him to perform a post-mortem examination. So statistician will tells you what are the mistakes that you have done, right? You could have collected the data in a proper way, this way, that way. So due to that, your data is not well, similar to that. So he will do a post-mortem. It's something similar to the post-mortem examination, and he may say why this experiment failed. So that's all statistician can say. Therefore, what we'll have to do is, before collecting the data, when you remember, planning is important, right? Planning. In the first course, we said that is the first lecture. Planning is important. So this formulating the experimental design is also planning, part of the plan, right? Even you draw the field layout, we call it as field layout, FIELD, field layout. Field layout, right? So field layout might say how many treatments, how many blocks. Let's say we have 4 treatment, T1, T2, T3, and so on. How we allocate all these treatment to all the plots will give the information about the design. Okay, right. Any questions? So these are very basic information about this design. Experiment in the field. Now, how we can do the experiment in the field? Doing experiment in the field is very difficult, because as I pointed out earlier, a lot of variability is there. All right, a lot of things has to be considered, right? So when you do experiments in the field, the experiment unit, right, it is the vehicle for evaluating the response of the material to the treatment, right? So please make a note of it. Last time I asked one question on quiz, so where I can remember what is experimental unit last year. So everybody has copied this. Vehicle for evaluating the response of the material to the treatment. So what do you mean by vehicle? So this is just a definition, right? So you can write in your own language, own phrases. Actually, it is the unit, experimental unit. It is the unit where we measure the response. It is the unit where we measure the response. For example, he said flux. Let's say I have the early example, 33 plants, right? That example. So here we apply T3, here we apply T2, here we apply T4, I think. Here we apply T1, 4 treatments. Now you see, to look at the response of T3, to look at the response of T3, I cannot go and measure what is happening here. To get the response of T3, I'll have to measure the plants in this plant. So that experimental unit. So to measure the response of that treatment, right? To measure the response of that treatment, I'll have to measure the plants in that particular plant. So that is called as experimental unit, right? So it is the unit where we measure the response of that particular treatment. Clear? Right. So that is called as experimental unit, which I have already explained to you as well. This experimental unit can have any shapes. So in the middle one is missing. I will explain it. First one is a rectangle. First one is a rectangle. So this is a rectangle, right? This is the most common one. Rectangle one is the most common one. You can have a square shape, that is also possible, right? Rectangle or square type. The second type is called as fan shape. Fan shape. Fan shape means you can draw that, huh? Something like this. We don't learn this design. We don't learn this design because it is a little bit advanced design. But I will just explain what it is. Right. Here, this fan design actually in this direction, the distance between, how do you call this? Arc. These are arcs, right? Arcs. So the distance between arcs, for example, this is the distance. Distance between the arcs will increase in this direction. I don't want to explain too much. So you have the radius for these arcs. So everywhere you get the, when arc and the radius meets, that is the place where we plant it. That is the place where we do the planting. So what is the use of this kind of design is studying the density. Somebody said density. Let's say, for example, this plot and this plot. Same size, 3 and 2. This is also 2. Here I am planting 20 plants in the same space. I mean, same space. Here I am planting 30. Is the density different or same? This is one situation. This is one situation. This is another situation. This situation 1. This situation 2. Tell me, is the density same in 1 between these two plots? Let's say A and B. You have to speak out, huh? No easy way to send chat. Yes, good. No, I'm asking, yeah, I'm asking just 2. once again, can you send it me, because it is I'm asking 1 and 2. 1 and 2. So in 1, the density is same or different? Yeah.
Different.
Yeah. In 1, density is different because yeah, if you calculate it, in 1 density is different. Why?
Area of the plot
Yeah.
is same,
Say
but
for this.
population different.
Yeah, for the same area you have different number of plants. For the same area you have different number of plants in number 1. What about number 2?
Same density.
Huh?
Same density.
Same density. Number 2 is same density. Why? If you
Um,
take
area
area,
double,
yeah,
population also double.
double. So the density is same. Density is given number of plants per unit area. Let's say number of plants per hectare. So that is how we measure the density. If you measure this way or this way, you will get the same number of plants. So density is same. But here the density is different. So if you calculate per hectare, because this 20 is only for 6 square meter. So if you convert it per hectare, this is for 34 only 6 square meter. You can convert it into hectare. Then you will have different values. So this is a different density. Right. So now this kind of study, this is called as fan design. This is called as fan design, fan shape or fan design. This is used to look at the density studies, or sometimes we call it as spacing trial. What do you mean by spacing trial? Spacing trial. Density studies or spacing trial? I will use another. Spacing trial. What is spacing trial? When you talk about spacing trial, let's say Chile. What is the spacing? Somebody said 30 into 60 centimeter. Let's say maize. What is the spacing? Anyone?
13 to 60.
13 to 60. Oh, we will take one more different one.
60 into 90.
Maize? Right.
60 into 90.
Is it maize or something else? 60 into 90, right. I am not sure, I couldn't remember all these figures. Right, somebody said 60 into 90 spacing. Right. How we determine the spacing for maize is 60 into 90, and for chili it is 30 into 60. How do we determine? Is it given by the Bhagavad Gita or Quran or Bible? Hmm?
Based
So
on the canopy size.
yes, based on the morphological characters of plants. So this is what called as the spacing is different. For example, if you start with the spacing, let's say if you start with the spacing mean rather than calling it as spacing, space mean the area, square meter. Sorry, it's 2, square meter. If you start with square meter, you will get a kind of graph like this. So this is the yield. If you obtain the maximum yield, this is called as optimum spacing. We'll have to write down. Optimum spacing. So this is maximum yield. You obtain the maximum yield. So for example, starting from 0, I'm talking about 0 into 0 spacing, that is 0 plus 0.01 into, as an example, into 0.01 meter. We multiply and see. Then 0.02 into example 0.02. So likewise 0.03 into 0.0. So likewise we can increase the spacing. We can go up to any number of spacing. Huh? So this is how we do the research, right? So this is called as spacing trial. Can you see how do you call this first spacing? How do you call this second spacing? There's a name for this, name for this, name for this, name for this. How do you call it?
Int.
Yeah. So which one intra, which one inter? Usually,
First one intra.
yeah. Usually the higher one will come as a
Inter.
inter, right? Higher one comes as an inter. The lower one comes as a within row spacing or intra spacing, right? So this is what we are doing here in this fan design. Fan design, which I have showed you earlier. I have erased it. Okay. So in the fan design, what is happening is so we plan in such a way. This, I mean, we'll have to draw it very carefully. Yeah? So I cannot draw it very carefully here because. So the distance between these arcs will increase in this direction gradually. You don't need the details and so on. So one is taken as inter, then between arcs. I mean, within arcs. All right. So actually, that is also changes. So in both ways, this way and this way, we can change the, we can increase or decrease the spacing. So that is how the spacing trial could be done. So that is why we are using this fan design. This is called as fan design. Right? It is called as fan design. Any questions? Any questions? Any questions? So you understood, right? Right. So that is about the fan design. The third type, sometimes you will learn this a little later. This kind of arrangement also there. We don't have this kind of, sorry. We don't have, we don't want to have this kind of square or rectangular part, but we want to have this kind. For example, if you are using a special machinery or irrigation, right? Look at irrigation first. You are doing some sprinkler irrigation testing. Normally, sprinkler, is it rotating in a circle or square? Is it rotating like this or rotate the space? How the sprinkler operates? So sprinkler rotating, isn't it? On a circle, not thin square. So we need this kind of plot for irrigation trials. Similarly, machinery. What is the problem with machinery here? Suppose, let's say I'm doing some plowing. I'm doing a small trial. You plow. Have you heard about puddling? How many of you have heard about puddling? No one? Whole agronomy is gone then. Puddling. What is puddling? Anyone? I'll have to ask question. I didn't bring the attendance sheet. I will ask the names appearing here. Dilini. What is puddling? You can answer in any language, no problem. What is puddling?
Madagara.
Oh, yeah. So, for what we do? For what crop we do?
Rice.
Rice, yes.
Paddy.
For yeah. Paddy, yes. Rice, paddy. For paddy, we do puddling. It's a kind of land preparation technique. Why? What is the purpose? Breaking down large soil colloid into small parts. So that is one objective. There are so many other objectives. Can you guess what are the other objectives? You cut and tear the weeds and incorporate into the soil. Then try to get a hard pan, especially for rice. We need a hard pan, isn't it? Why? To reduce the water penetration. So likewise and so on, right? Doesn't matter. Now I am doing a small experiment on this puddling. So I'm doing a small experiment with the tractor. First field is I'm puddling with 6 inches. I'm puddling with 9 inches. I'm puddling with 12 inches. Do you understand? So we can adjust the machineries accordingly as we want. Right, 6 inches. You might have seen the tilling. I mean, the puddling wheel and how this tilling and everything is done using tractors. Right. So this is my experiment. How whether this depth is good or whether this 9 inches depth is good or whether 12 inches depth is good. That is what I am going to test it. So in that case, right, if I have square plot, what is the problem? Tractor goes and tractor cannot reach the corners especially. So it has to turn before reaching the corner. So these areas will be not in the experiment. So anyhow, when you, let's say you are doing broadcasting, definitely the plants will grow here as well. The seeds will be thrown here as well. So if you get the yield from that, that will be not really due to the puddling. Because of this, machinery cannot turn, so that we have a circle. If it is circle, tractor, without any problem, it can travel. Isn't it? Right. So that is how the circle plot is equal. Right. The other one is border effects. You can read the things, but I will just talk about what is this border effects. Let's say the earlier example, what are these T1, T2, T3, T4? I'm doing
Chili.
Yeah, chili with 4
Fertilizers.
fertilizer 4. Now I have here spacing 3 into 2. Now I'm arranging. I'm just showing by number. Don't worry. How many plants we can accommodate? That we said
33.
33. Right. Now the spacing is same. Spacing is same. So no problem. Spacing is same. T3 here. T2. What is T3?
Organic fertilizer.
No. T3 is
T3.
Organic fertilizer with 50% inorganic.
yeah. T2 organic plus
Organic
25.
25%.
Good. Right. Now, what is the problem here? What is the problem? Because this is T3, this is T2. What is the problem here? If you design, what is the problem here? Look at these plants, especially this plant, this plant, this plant, as an example, right? Similarly, this plant, this plant, this plant. Can somebody tell me what is the problem with only the plant which I have indicated? Others will not have, in this example, will not have the same effect as the one which I have identified. Yeah? What is the problem? This is actually because this is a fertilizer. Once the fertilizer is dissolved, can you stop this fertilizer's movement? There may be movement of fertilizer from this area to here or this area to here. There are possibilities. When there's water, movement of water, then how do you call the water movement from this to here and this to here? Scientifically, agriculture term, there's an agriculture term. Water moving not on the surface, because we have the earth walls or boundaries. Boundaries are there, so they cannot move on the surface. The water cannot move on the surface. Water will move beneath the surface, underneath the surface. So how do you call this phenomenon? Anyone? Agriculture engineering group.
Seepage.
Seepage, yes. This is called as seepage. Right? You have learned this, right? Seepage. So underneath the ground, the water can move. So if there is no barrier, because underneath you don't have any barrier. Only above we have the barrier, earth wall. Right? In Tamil, Varambu, in Sinhala, nearer. So we can have Varambu or nearer above soil, but not underneath. Underneath, there is a possibility to move. So this is the biggest problem in this kind of experiments, fertilizer, especially fertilizer. So the fertilizer can move either way. We don't know which way is possible. Either way is possible. So because of that, the plants in the very corner, which is called as border plants. This is called as border effects. This plant will show a different growth pattern compared to the rest of the plants. This shows a different growth pattern compared to the rest of the plants. So that effect is called as border effects. That effect is called as border effects. For example, how we can reduce the border effects? One thing, we can remove, we can keep this plant, right? We can keep this plant until the research is over. But for our analysis, we can ignore this row, we can ignore this row, we can ignore. Similarly, this row we can ignore without considering. Similarly, this row also we can ignore, and so on. Right? So that is the best way. The second way is how we can reduce the seepage, how we can avoid the seepage. We can avoid the seepage by putting a polythene underneath. That is also possible. So people do some research, but in fixed like in Philippines, Rice Research Institute, they have concrete walls between the plots, permanent concrete walls, so that no seepage, especially for this kind of study, right? Fertilizer studies. So we'll have to stop all this. So this is called as border effects, right? Clear? So we cannot take the border plants. Border plants cannot be taken. Why? Plants along the edge of the plot, which I said, perform differently than those in the center of the plot. You got it? Why? Yeah. So not only that, sometimes all these, let's say we have trees, right? Let's say in this field, I have a field. Big trees are there closer to the field, right? Now, what will happen if there's a shade? So these border plants will be affected. All right. So that we should avoid. Border plants has to be, ignored, or the plants which is on the edge has to be ignored. Border rows, this is what I said, border rows, edge on the in the field or end of the plot have an advantage, less competition over the resources. As I said here, the plants, the other reason is, let's say the border rows here. So if you look at, I will consider only this situation. If you consider these plants, these are also rows. If you consider that plant, they are having competition. They are having competition. But if you look at this row, they don't have any competitors, neighbors. So less competition. So that is how it indicated, right? Plants on the perimeter mean, so closer to the boundary, perimeter of the plot can be influenced by plant height or competition from adjacent plots. I mean, could be circular plot or could be square plot. Machinery can drag the effects on one treatment into the next plot. Fertilizer or irrigation can move from one plot. This is what I said, right? One plot to the other. So impact of the border effects is greater with very small plots. If it is a big plots, the impact is less. So here also, when you plan this experiment, you have to plan it properly, because you see, if I have 33 plants, if 16 plants are on the border, I want to remove all the 16 plants. So if I remove all 16 plants, right? If I remove all 16 plants, only another 17 plants inside the border rows. So this only can be used for analysis. These are the only plants that I can use it for analysis. The border effect plants, I cannot use it for any purpose. So you see, when you plan your design, you have to plan it for, leave some plants for border effects as well. So we'll have to plan it in proper, right? Right. Last slide. Maybe, yeah, we will talk about this also, and then we will minimizing the border effects. How we can minimize the border effects? Leave the allays between plots. So that means if you have the plots, right? Suppose, let's say, if you have a plot, 2 plots, you have to give some good enough space. This is called as alley, right? Alley mean maybe single කානුවක් දාන්න පුළුවන්. In Tamil ஒரு சின்ன காணுண்டு விடலாம் இது ரெண்டு முறையில், so that seepage நடக்கும். So you don't get any seepage, right? So between plots, some kind of barrier, alley cropping Can you remember, Alice? Remove plot H and measure the yield only on center portion. So that is what I said earlier. If you have border plants, don't take that plants for the analysis. Only take the middle part of it. Plant border plots surrounding the experiment. So purposefully we plant some plants for border effects so that we can avoid the border effects also when you plant it. Right. Any questions? Any questions? Any questions? Right. If there's no questions, we will stop it then. Okay. Thank you then. See you next week.